Welcome, everyone. Ready to dive into something really cool. We're going to be talking about magnetars today. And get this, they're the most magnetic objects in the entire universe.
Out there in the vastness of space.
Can you imagine? We're going deep with this, working from some pretty intense research.
A lot of information packed in there, yeah?
But by the time we're done, you'll know exactly what a magnetar is.
And not just what they are.
Right. But why astronomers are so fascinated by them.
Some of the most extreme physics you can imagine.
For sure. So to kick things off, let's get the basics down. What exactly is a magnetar?
All right, well, they're a type of neutron star. And those are what's left over after a huge star goes supernova.
Like the star's core collapses in on itself, right?
Yeah, you're talking about something the size of, say, a city.
Wow.
But with the entire mass of the sun.
So incredibly dense.
Dense doesn't even begin to describe it.
I bet.
But here's what sets magnetars apart. Their magnetic fields.
Ah, yes.
I'm talking trillions of times stronger than Earth's magnetic field.
Trillions.
That's wild. To give you an idea, if you had a magnetar as close as the moon,
Oh, wow.
it could wipe your credit cards clean from here.
No more online shopping then, haha.
Oof, gone.
So those magnetic fields are a huge deal, but did astronomers always know these things existed?
No, not at all. It took a long time to even figure out what they were looking at.
I can imagine.
You see, back in the 1970s, astronomers started picking up these powerful bursts, X-rays and gamma rays, nothing like they'd ever seen.
Sounds mysterious.
They called them soft gamma repeaters, SGRs for short,
SGRs, got it.
and anomalous X-ray pulsars, or AXPs.
So all these weird signals, but no clue what was causing them.
Exactly. Took more observations, more time to realize that both SGRs and AXPs were actually coming from the same type of object, the ultramagnetic neutron stars we now call magnetars.
Feels like cracking a cosmic code.
Yeah, kinda.
So we know they're super magnetic, but what else makes magnetars so interesting?
Well, one thing is they're active across the whole electromagnetic spectrum.
Oh, wow.
I mean, radio waves, infrared, optical light, X-rays, gamma rays, the whole shebang.
That's a lot of energy coming from something the size of a city.
Oh, yeah, and that energy isn't always steady either. Magnetars have these, let's call them transient events.
Transient events.
Basically, imagine a cosmic tantrum.
Love that analogy, a cosmic tantrum.
There are three main types. You've got short bursts. These happen all the time, last a tiny fraction of a second,
Fast.
and pack the energy of 100 suns.
Whoa, okay, those are intense.
Then you have intermediate flares.
Right.
These are a bit rarer, last longer, and they actually show us the magnetar's spin.
Like a lighthouse gone wild in space.
You could say that.
I like it.
And then the big ones, the giant flares.
Oh,
Only 3 recorded so far, but they're brighter than anything else in our galaxy besides supernovae.
no way.
Yeah, there was one in 1979, briefly messed with Earth's upper atmosphere, and that was from halfway across the galaxy.
That's some serious long-distance power.
Right. Now, besides these flares, magnetars also go through these longer phases. We call them outbursts. Can last weeks, months, even years.
Wow.
Each one unique, giving us clues about how these objects behave.
So it sounds like magnetars are always putting on a show.
You could say that.
But what's actually happening inside these things? What makes them tick?
Ah, now that is the really fascinating part.
Perfect. I'm all ears.
To understand what's going on, we have to look at the light they emit, their spectra.
Spectra.
It's a mix of thermal emission, which is just heat from their surface.
Makes sense. They're incredibly hot.
Incredibly. And then there are non-thermal processes driven by their magnetic fields, those twisted, intense magnetic fields.
It's not just heat. The magnetic energy shapes the light we see.
Exactly. And recent measurements with a satellite called IXPE
IXTE.
showed us that the light from magnetars is highly polarized,
Oh, interesting.
meaning it vibrates in a specific direction.
Ah.
Exactly what we'd expect with such strong magnetic fields.
So polarized light is like a fingerprint of their magnetism.
In a way, yeah. One magnetar in particular, 4U0142 plus 61, showed this dramatic shift in polarization angle. As the energy of the light changed, a 90-degree shift.
A 90-degree shift. That's wild.
Tells us the surface, the magnetic field structure. It's more complex than we thought.
So those magnetic fields, we know they're super strong. But what else can you tell me about them?
Well, they do decay over time.
Like a battery losing its charge.
Kind of. And to understand how that works, we have to get into some pretty exotic physics.
Okay, hit me with it. I love this stuff.
So for this decay to happen, the magnetic field needs something to push against, right?
Resistance.
Right, and we think that's a super dense layer in the magnetar's crust,
Deep inside.
made of something we call nucleopasta.
Nuclear pasta. Now, that's a term I haven't heard before.
Imagine atomic nuclei squeezed so tight they look like different pasta shapes.
Whoa.
Spaghetti, lasagna, gnocchi, you name it.
That's incredible. Nuclear pasta.
This pasta creates resistance, helps the magnetic field decay.
Wow.
It also affects how the magnetar behaves.
Okay, so we've got these ultra-dense stars, super strong magnetic fields that are constantly changing,
Yeah.
and we think they're powered by nuclear pasta.
It's amazing, isn't it?
This is getting pretty wild. So what about those magnetar tantrums we talked about, those bursts and flares? What triggers those?
Well, there are a couple of main theories, and both involve the incredible forces at play inside a magnetar.
Okay, let's hear them.
The first one focuses on starquakes.
Starquakes, so like earthquakes, but on a star.
Precisely. You see, the magnetar's crust is solid, but it's under immense pressure.
From that magnetic field.
Yeah, exactly. And as the field shifts and evolves, it can actually cause the crust to crack.
Like tectonic plates shifting here.
Just like that.
And those cracks release energy.
A massive amount of energy, yeah, in the form of seismic waves, which we think could be triggering those short bursts.
Ah, that makes sense. So what's the other theory?
This one's all about the magnetic field itself.
Okay. Remember those twisted field lines we talked about?
Yeah?
Well, they can get so twisted, so tangled, they become unstable.
Almost like a rubber band, you stretch it too far.
Yeah.
And it snaps.
Perfect analogy. Except here, the snap unleashes a huge amount of energy. We call them magnetic reconnection events. Magnetic reconnection events, okay?
And these are another likely source of those magnetar tantrums.
So internal stress causing starquakes and tangled magnetic fields causing these reconnection events.
Right.
It's incredible how much is happening inside these tiny objects.
It really is. And what's even more exciting is that magnetars might not just be throwing these little tantrums.
What do you mean?
They might actually be the driving force behind some of the most energetic events in the universe.
Hold on. Are you saying these magnetars are influencing events even bigger than those giant flares?
That's exactly what I'm saying. There are potential links between magnetars and things like compact binary mergers, fast radio bursts, gamma ray bursts, even superluminous supernovae.
Whoa, slow down. I need a minute to process all of that. Let's
Yeah.
start with compact binary mergers. What are we talking about here?
Picture two neutron stars.
Okay.
Already incredibly dense, locked in a gravitational dance, spiraling closer and closer.
Sounds intense.
It is. Their gravity warps space-time, creating ripples that spread out as gravitational waves.
Which we can detect here on Earth.
With instruments like LIGO and Virgo, yeah.
Like listening to echoes of these cosmic collisions.
That's a great way to put it.
Incredible. But where do magnetars fit into all of this?
Well, one theory suggests that when these two neutron stars finally merge, they could create a temporary magnetar.
Temporary magnetar. Interesting.
This newborn magnetar would be incredibly energetic with a super strong magnetic field, and that could be what powers the afterglow we see after the initial burst of gamma rays.
So the magnetar is like the encore to the main event.
Yeah, exactly. And by studying that afterglow, we can learn more about what happens during these mergers.
Wow, okay, one cosmic connection down. What about those fast radio bursts? I've always found those mysterious.
Fast radio bursts, or FRBs, are definitely some of the most puzzling things out there.
Yeah.
They're super brief, super bright bursts of radio waves.
Coming from really far away.
Distant galaxies, and we're still trying to figure out exactly what causes them, but one leading theory points to...
Let me guess. Magnetars.
You got it. Remember those giant flares?
Yeah.
Imagine a magnetar in a distant galaxy unleashes one of those.
Okay.
Some of that energy could be focused into a beam of radio waves.
Traveling across space.
And when that beam sweeps past Earth, bam, we see it as an FRB.
So it's like a lighthouse beam, just incredibly powerful.
And we have some evidence to back this up.
Really?
Back in 2020, a satellite called Integral detected a powerful X-ray burst from a magnetar in our own galaxy, SGR 1935 plus 2154.
Is that the same one that messed with Earth's atmosphere back in the 70s?
Not the same one, but same family, a soft gamma repeater. But what made this observation so important was that they detected the X-ray burst at the exact same time and from the same place as a powerful FRB.
Well, like a smoking gun.
It was huge. Really strengthened the idea that magnetars are behind these FRBs.
Okay, so we've got compact binary mergers, fast radio bursts, both potentially linked to magnetars. What about gamma ray bursts? Those are even more energetic, right?
They are. Gamma ray bursts, or GRBs, are the most powerful explosions we know of.
I can only imagine.
In just a few seconds, they release more energy than our sun will in its entire lifetime.
Mind-blowing. What could possibly create that much energy?
There are a few theories, but one possibility is, you guessed it,
Magnetars.
magnetars. The energy stored in their magnetic fields is colossal, and if even a tiny fraction of that is suddenly released.
It could power a GRB.
Exactly.
So, yet another cosmic event potentially driven by these magnetar powerhouses.
Mm.
But are there certain types of GRBs that seem more likely to be magnetar-related?
Yes, actually. We classify GRBs based on how long they last. Long-duration GRBs, they can last from a few seconds to several minutes.
Right.
We think these happen when a massive star collapses, forming a black hole.
Right.
But sometimes, instead of directly forming a black hole, the collapsing star might create a rapidly spinning, highly magnetized neutron star. A magnetar.
So the magnetar is like a stepping stone to the black hole.
Yeah, and that magnetar, with all its energy, could be what powers the long gamma ray emission we see.
That makes sense.
Oh.
What about the short-duration GRBs?
These are much shorter, typically less than 2 seconds.
Yeah.
We think they happen when two neutron stars, or a neutron star and a black hole, merge together, like those compact binary mergers we talked about.
Oh, right. So magnetars could be involved in both types of GRBs.
That's the thinking. Whether it forms during a star's collapse or from a merger, a magnetar could be the key to powering these incredibly bright events.
This is fascinating. Magnetars seem to be connected to so many extreme events in the universe. Compact binary mergers, fast radio bursts, gamma ray bursts.
It's pretty amazing.
What about those superluminous supernovae we mentioned? How do those fit into the picture?
So, superluminous supernovae, SLSNA for short.
SLSNA, got it.
They're like supernovae, but amped up, way brighter.
How much brighter are we talking?
Like 10, even 100 times brighter than regular supernovae.
That's a huge difference. What makes them so luminous?
That's the big question, and well, magnetars might hold the answer.
Magnetars again.
It all comes back to them. Think about all that rotational energy, the magnetic energy we talked about.
Okay.
As a newborn magnetar spins down, it releases some of that energy.
Uh-huh.
And that energy can interact with all the material that got ejected from the supernova explosion.
So like the magnetar is giving the supernova an extra boost of energy, making it even brighter.
Exactly. That extra energy from the magnetar could be why SLSNA are so incredibly luminous.
Wow, this is amazing. It really seems like magnetars are connected to all these extreme energetic events in the universe.
They really do. Compact binary mergers, fast radio bursts, gamma ray bursts, superluminous supernovae. It's like they're the ultimate cosmic power source.
Absolutely. And the craziest part is we're just scratching the surface, right?
Oh yeah, there's so much we still don't know about magnetars, like their internal structure, how their outbursts work. All these details we're still figuring out.
That's what makes studying them so exciting. It's like we're exploring a whole new frontier in astrophysics.
Every new observation, every new discovery, it's bringing us closer to understanding these fascinating objects.
Well, this has been one of the most incredible deep dives we've done. We went from the basics of what a magnetar is all the way to exploring their potential role in some of the most powerful events in the cosmos.
It's been a pleasure exploring the world of magnetars with you.
And with our listeners, of course. I know we've covered a lot. Probably left you with as many questions as answers.
That's the beauty of science, though, isn't it?
Always more to learn, always more to discover.
Thanks.
So to all our listeners out there, keep those questions in mind. Keep looking up at the night sky. And who knows what incredible discoveries are waiting for us in the future. And that is where we leave you on this deep dive.